Hello and welcome. Today we're going to talk about RabbitMQ. RabbitMQ is one of the most popular message brokers used in modern applications. So knowing this technology is absolutely crucial. In this video, I will explain the fundamental concepts of RabbitMQ and walk you through some practical examples so that you understand how message brokers actually work. Without further ado, let's dive in. So first of all, we're gonna discuss producers and consumers. In a message broker system, we have a producer, which is a program or microservice that sends requests, and a consumer, which is another program that consume or process the request. An application can be both a producer and a consumer. The application on the left can be changed to a consumer, and the one on the right can be a producer. Usually, a producer will not send a single message, it will send a bunch of them. But the consumer will not process all of them at the same time. So messages are stored in something called a message queue. So the first step is to install RabbitMQ. There are two ways to do it. You can either download RabbitMQ directly to your local machine or use a Docker image. In this tutorial, I'm going to use Docker. So to download RabbitMQ, you can run docker pull RabbitMQ 3 management. So this is the version of RabbitMQ that allows you to interact with the UI. I already have it on my machine, so I don't need to do that anymore. But if this is the first time you run RabbitMQ, you have to run this. So to verify if you have the image in your local machine or not, you're gonna run docker images. So as you can see, I already have the 3 management version of RabbitMQ in my local machine. So once you already have the image, it's time to run a container. You can run this command. So docker run will run an image and create a container. -d means we're gonna run in a detached mode. -name RabbitMQ means the name of the container is RabbitMQ. -p means we're gonna map the port of RabbitMQ to my local machine. 5672 is for the RabbitMQ server, and 15672 is for the RabbitMQ UI. The package is RabbitMQ, and the tag is 3 management. So let's run this. We already have a container here. So if I open up the UI of Docker, I'm gonna see a container running. So once you finish your setup, it's time to write some code. I will upload all of this code to my GitHub account, so you feel free to check it out after watching this video if you want to study it in more details. So in the producer, the first thing to do is import the Python library. So this is a library that RabbitMQ recommends to create a connection with the server. Next, we're gonna create a connection with the local host. So because we are running everything on our local machine, so we have to use the local host instead of other hosts. Next, we're gonna declare a queue. As I mentioned before, a queue is a place that receives the message from the producer. So the name of the queue here is hello. So once the producer has a queue, he needs to publish the message. So we're gonna run channel.basic_publish. This function takes an argument called exchange. I'm gonna explain this concept later on this video, so don't worry too much about it right now. Right now, we leave it as an empty string. The routing key is gonna be the name of the queue, and the body is gonna be the message. So we're gonna send hello world to the consumer. Then at the end, we're gonna close the connection. So on the consumer side, the first thing we do is also import all the libraries, including Python. Then we're gonna create a connection just like the consumer. Here we're gonna declare a queue. So technically this step is not really necessary if the queue already exists, but we don't know whether or not we will run the consumer first or the producer first. So it's a good practice to redeclare the queue inside the consumer. Here we're gonna define a callback functions. So this function will be triggered once the consumer receives the message from RabbitMQ. Inside of this function, we only need to print out the body or the message. And then we're gonna subscribe the consumer to the hello queue by running basic consume. The queue name is hello. We're gonna pass in the callback function, and auto acknowledgement is true. So I'm gonna explain this more later on. And then we're gonna start consuming messages. So let's run this. The first step is running the consumer. So I'm going to run python receive.py. Then I'm going to run the producer. So python send.py. So we can see that the producer already sent a string called hello world. So now when we go back to the previous tab, we see that the consumer already received a string. Next, let's talk about task queue. The main idea behind task queue is to avoid doing a resource-intensive task immediately and wait for it to complete. Instead, we schedule it to use later. Work queues are often used to distribute tasks among multiple workers. When we run many workers, the task will be shared between them. There are two ways that a task will be distributed across the workers. The first one is a round-robin fashion. So RabbitMQ will send a message to the next worker in the sequence. Here, in the example, the producer sent out 6 messages to the queue. And on the other side, we have 3 consumers. And if we follow the round-robin fashion, the first and the fourth messages will be distributed to the first consumer. The second and the fifth messages will be distributed to the second consumer, and the rest will be distributed to the third consumer. But round-robin dispatching is not a great way to distribute the tasks because let's say we only have 2 consumers, and the tasks at the odd positions are heavy, while the tasks at the even positions are light. That means the first worker will always be busy, while the second worker is free most of the time, and we don't want that. That brings me to the second way of dispatching called fair dispatching. So essentially, we only distribute one task to a worker at a time. A worker cannot take another task until it finishes the current task. So for example, let's say we have 6 tasks here, and the first, the third, and the fifth tasks are light, while the rest are heavy. On the right, we have 2 consumers, and here's an example of how we can distribute the tasks. So each consumer receives some amount of light tasks and some amount of heavy tasks. So the work distributed between them are quite even. So the next concept I want to mention is message acknowledgement. You may wonder what if a consumer dies before it completes a task. So far, we don't have any tool that can prevent that loss. That's where message acknowledgement comes into play. An acknowledgement is a way for a consumer to tell RabbitMQ that the message has been processed and received, so RabbitMQ is free to remove it. If a message dies without sending an acknowledgement, RabbitMQ will requeue the task and redeliver it to the next consumer. Message acknowledgement does happen when a consumer dies, but what if the RabbitMQ server stops? Our messages are still lost. The solution to this problem is message durability. So basically, we create a durable queue and make our messages persistent. To illustrate the idea of task queue, I have prepared some other code here. The first one is new task. So this is a producer. And the second one is a worker, which is a consumer. So what do we do inside of this producer and consumer? As inside the producer, the first thing to do is going to import the Python library and then create a connection with the local host just like before. And here we also declare a queue. The message here is either provided in the argument, or if there's nothing in the argument, we're going to return a string called hello. And the producer also sent a message to a default exchange, and the queue here is going to be hello. So we're going to pass in the message as the body. So for the consumer, the first thing to do is also create a connection with the RabbitMQ server and declare the hello queue. Then we're going to declare the callback function. But this function is a bit different from the previous one. So we're going to print that we have received the message. But here, what we do is that we're going to take the message and extract some dots, and the number of dots in the message will be the time it takes to finish the task. So let's say we have message ... That means it takes 3 seconds to finish the message. If we have message ... That means it takes 1, 2, 3, 4, 5, 6, 7 seconds to complete the task. Because I don't have any resource intensive task right now, so this is a perfect illustration. Once the task is finished, I'm going to print done and send an acknowledgement to RabbitMQ that the task is finished. At the end, we're going to run basic consume and we're going to connect to the hello queue. And on this function, we're going to pass in the callback function and then start consuming. So I'm going to run two workers to illustrate this. So the first worker is Python worker. So this is the first worker. We have the second worker. And now once we have two workers, I'm going to run a producer. So the first message has been sent. Then the second message. Then send the third message. And the fourth message. So when I check back to the consumer, we can see that the first and the third message is received by the first worker. And the second and the fourth message are received by the second worker. So this is the round robin distribution. But what if we send a message that takes a lot of time at odd positions, but most of the messages in even positions are light? So for example, the first message take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds to finish. So I'm going to send it. While the second message only takes 2 seconds to finish. The third message takes more than 10 seconds to finish. While the fourth message only takes 1 second to finish. With this setup, the first message and the third message is also distributed to the first worker, right? So that means the first worker is very busy, while the second and the fourth message are distributed to the second worker. So he's pretty free, right? He only takes 3 seconds to finish all the tasks. So how can we fix this? So that's where fair dispatching comes into play. So to include fair dispatching, I'm gonna include this line here, channel.basic quotes. So it uses a protocol that allows RabbitMQ to distribute a task evenly. I'm not going to get into the detail of this, but if you want to learn more about this protocol, feel free to Google it and learn. So I'm going to restock my worker and show you how fair dispatching works. So I'm going to cancel this. Cancel this. So I'm going to run two workers again. So Python worker.py. So now I'm going to run the producer. The first message is going to be a very time-consuming message. The second message only takes 2 seconds to finish. The third message is also time-consuming. And the fourth message only takes 1 second to finish. So you can clearly see that now the first message and the fourth message is distributed to the first worker, because the first worker takes a very time-consuming task. When the second worker finishes the second message, he's available to take the third message. And that's why the second and the third message go to the second workers. But right now, there is no guarantee that a message is not lost if a consumer dies or if we restock our RabbitMQ server. To prevent that, first, we have to make our queue durable, and secondly, make our message persistent. So to create a durable queue, we have to declare the tag called durable.true here. So I'm going to create a new queue called task queue. The reason why I'm not making the hello queue durable is because RabbitMQ doesn't allow us to change the status of a queue once it's created. So I'm going to comment this out. In here, instead of listening to the hello queue, I'm going to listen to the task queue. On the producer side, we do exactly the same. So we're not going to redeclare the hello queue. And we're going to create a new queue called task queue, and it is a durable queue. And at the end, instead of just send a normal message, I'm going to make the message persistent. So I'm going to send the message to the task queue. In this function, we can provide a properties attribute. And in this property attributes, we're going to make the message persistent. So let's try this. I'm going to run 2 workers and then show you how message durability works. So first, I'm going to send a very time-consuming message. So this message is received by the first consumer and not the second consumer. So what if I cancel this consumer? So the first consumer dies. Then the message is automatically distributed to the second worker. So what if I run the 2 workers again, send the message to the first worker, but now I restart the RabbitMQ server. Let's try that. So I'm gonna have this worker here, Python worker, and I'm gonna send a very time-consuming message. Then in the Docker desktop, I'm gonna stop the server for a while. So you can clearly see that it says Python exception connection closed by broker. So that means we already closed the connection to the RabbitMQ server. So if I enable the server again, then I run a consumer or a worker. So we can see that the worker continue to pick up where it's left off because the queue still exists in the RabbitMQ server. Usually, a producer will not send messages directly to consumers. In reality, producers aren't even aware that the consumers don't receive the message. Instead, producers send messages to an exchange. An exchange receives messages from producers and pushes them to the queues. The exchange must know exactly what to do with the message it receives. It uses the rules defined by the exchange type to deliver the messages. Each exchange has a binding relationship with the queues. The relationship has a binding key, which will be used to match the routing key of the message. We're going to discuss this later on this tutorial. A queue can have multiple bindings with the exchange. There are 3 basic exchanges: fan out, direct, and topic. Fan out exchange is the easiest one. It basically ignores the binding rules and broadcasts the message to all available queues. The direct exchange is like a sniper. It sends the message to the queue that has the binding key, matches the routing key of the message. The topic exchange is quite similar to the direct exchange, but the routing key of the message must be a list of words separated by dots, and the binding key of the queues must have the same pattern. But there are 2 exceptions here. The binding key can contain an asterisk, which represents exactly one word. So in this example, we have asterisk dot orange dot asterisk. That means we can put any word before orange and any word after orange. The second exception is the hash symbol. A hash means 0 or more words. As an example, we have lazy.hash. That means we can put any number of words after lazy or none at all. So let's go over some examples for each exchange. The first one is a fan out exchange. So in the fan out exchange, the message is broadcast to every available queues. We have some code for the consumer here. So the first thing, as always, create a connection. Then we're gonna declare a fan out exchange. So the name of the exchange is logs, and the exchange type is gonna be fan out. After that, I'm gonna create a temporary queue for each consumer. If you don't provide the name of the queue when you declare the queue, RabbitMQ will automatically create a new queue for you. And the name of the queue will look something like this. And we provide the exclusive test. That means this is a temporary queue. That means when we cancel the consumer, the queue will be lost. And to access the name of the queue, we can run result.method.queue. So next, we need to create a binding between the exchange and the queue. So as I mentioned before, a binding is a relationship between the exchange and the queue. So we need to map them together. So we're gonna run channel.queueBind, provide the name of the exchange and the name of the queue. Then I'm going to define a callback function. So this function will bring out the body of the message, and then we start consuming. So provide the name of the queue, provide a message callback, and automatically acknowledge when the message is finished processing. The second file I have here is emit log fanout. So this is a producer. First of all, always create a RabbitMQ server, then create a fanout exchange, then get the message from the terminal or create a default string, so info hello world, then publish the message to the exchange. So we're going to provide the name of the exchange, in this case logs. The routing key is nothing because in fanout we don't care about the routing key of the message, and the body is going to be the message itself. So let's try this. Let's say I create two workers. So let's say I create two consumer. And now I'm going to run the producer. So the producer just send a message called hello world to every single consumer. So you can check the terminal here. The first consumer received a message, and the second consumer also received a message. Before I move on to the next exchange, I want to show you the UI of RabbitMQ so that you can easily check the information of the queues and exchanges. Open up your browser, go to http localhost 15672. This is the port that you connect your local machine to the RabbitMQ UI. So the username is going to be guest and the password is also guest. Login. So to see all available exchange in your machine, you can click on exchanges. So we can clearly see that we have an exchange named logs, right? And this is a fanout exchange. To see more information about it, you can click on this link. So we can see that because we have two workers, right? So now we currently have two queues. Next, let's discuss the direct exchange. So as I mentioned before, the direct exchange will route the message with the binding key, match the routing key of the message. So here we have a consumer for the direct exchange. The first thing to do is also create a connection with the RabbitMQ server, then declare a direct exchange. So the name of the exchange is direct logs. Next, we're going to create a temporary queue for each consumer. So because this is a log system, right, it contains several severities. So the severity can be info, warning, or error. So for each severities, we're going to build a binding rule with the exchange. So we're going to loop through all available severities that the current queue have and bind that with the exchange. So as I mentioned before, we can have multiple binding between an exchange and a queue. We have a callback function that will bring out the routing key and the body of the message. And then we start consuming. So we're going to provide the queue name, the callback function, and start consuming. We also have a producer here. So the producer will create a connection with the RabbitMQ server. Then we're going to declare a direct exchange. The severity here is going to be either info, warning, or error. And if there's nothing provided in the terminal, we're going to use info instead. A message is also a list of terminal arguments. And if nothing is provided, we're going to use the string hello world. Then we're going to publish the message to the direct exchange. So the exchange is direct logs, the routing key is going to be severity, and the body is going to be the message. So let's try this. So I'm going to run two workers or two consumer. The first one only take warning and error message. So that's why I provide warning and error here. The second one accept all kind of messages, info, warning, and error. So I'm going to send two types of messages from the producer. So the first one is an error message. So when we go back to the terminal of the consumer, we see that each of them receive this message, right? The reason being both of these consumers have the error severity in their binding rules. So the direct exchange will route the message to all these queues. For the next message, I'm going to run an info message. You can see that the first worker doesn't receive the message because we don't have the info binding with the queue. On the other hand, the second worker received the message because we do have an info binding with the queue. So if you open up the browser, then go to the Exchange tab and then hit refresh, you can see that we have the direct logs exchange here, and it is a direct exchange. So when we click on this, we have 5 binding rules available, right? So the first worker have 2 binding rules, error and warning, and both of them are mapped to the same queue. The second worker have 3 binding rules, error, info, and warning, and all of them map to the queue of the second worker as well. Finally, we're going to talk about a topic exchange. So this exchange is quite similar to the previous exchanges. The only difference is the binding rule and the binding key. So first, we're going to declare a topic exchange, then create a temporary queue for each consumer. We're going to collect all the binding keys from the terminal. Then for each binding key, we're going to create a binding rule with a topic exchange. And in the callback function, we only return the routing key and the body of the message, and then we start consuming. On the producer side, we also declare the topic exchange, then get the routing key. So we can see that the routing key must be a list of words separated by a dot, right? So if there's nothing in the terminal, we're going to use anonymous.info. We get a message and then publish the message to the exchange. So before we run, I want to talk about the binding key a little bit. So the binding key contains 2 parts. The first part is called facility. So this is a facility that have the error message. It can be the application or the kernel. And the second one is severity. So severity can be critical or normal. So I'm gonna run 4 consumers. So this consumer will accept any kind of messages, right? Because we use a hash as the routing key. The second consumer received the message from the kernel. So it doesn't matter if the message is critical or not. As long as the message is from the kernel, this consumer will take care of it. The third consumer only receives critical messages. The final one is this. So this consumer have multiple binding rules. So the first rule is that any message from the kernel will be taken care by this consumer. And the second rule is that any critical messages will also be taken care by the current consumer. So I'm going to publish several messages from the producer to show you how it works. So the first one is this. So I'm going to run a kernel critical message from a producer. So we can see that this one received all kind of messages, so it should receive it. This consumer received all kernel messages, so it should receive this message. This one received all critical messages, so it should receive it. And this one received both kernel messages and critical messages, so it should receive it too. Now I'm going to run this command. So I send a critical application error message to all of the consumers. The first one, as always, will receive the message. But the second one don't receive a message anymore because this is an application messages, not a kernel message. The third one will receive it because it is a critical message. And the final one as well will receive it because it is a critical message. And finally, I'm going to run this message. So we're going to publish a normal application message to all the consumers. The first one, we absolutely receive it. But the second one don't receive it because it is not a kernel message. The third one as well, because this is a normal message. And the final consumer will not receive that as well because it is neither a kernel message nor a critical message. So the only consumer that receives this message is the first consumer. That's it for this video. I hope you enjoy it. If you like the video, please like and subscribe. That supports the channel a lot. And I will see you in the next video. Peace.